Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson 5 on tangents to circles. So this is kind of exciting. We're going to be introducing a new idea when it comes to circles. Maybe an idea that you played around with a little bit in Algebra 1, but you would have been doing it then with parabolas. Here we're going to be looking at, with circles, these objects called tangents. So let's take a look at what a tangent is. All right. We've now studied many theorems involving chords within a circle. Another important concept is that of a tangent to a circle. So let's take a look at what a tangent is. A tangent is a line or line segment that, no matter how far extended, will intersect the circle exactly once. In the picture shown, line M is tangent to circle O at point A. All right, so all of this is kind of important, but subtly important, right? We've got a circle, and we've drawn a line, right, tangent to the circle. Now what that means is that the line and the circle share one and only one point, and it's what's called the point of tangency. That's what we mean when we say it's tangent to circle O at point A. It means that point A lies on line M, and it also lies on circle O, but there is no other point that they have in common. The line is not going to intersect the circle anywhere else. Now, tangents to circles and other curves are very important in physics. One of the most important properties will be illustrated in the first exercise. So let me bring exercise 1 up to the top and let's take a look. In the following diagram, lines M and N are tangent to circle A at points B and C respectively. Letter A, draw in radii AB and AC. Awesome. Well, go ahead and take your straight edge, ruler, whatever, and draw in those two radii. Pause the video now and go ahead and do that. All right, simple enough. Let's get them in there. There they are. Now letter B. What appears to be the relationship between the radii you drew in A and the tangent lines they intersect? All right, so what do you think is the relationship between each of these radii and the tangent lines that they intersect? Pause the video right now. Now this is pure speculation. We'll prove it in a little bit, but right now speculate on what you think the relationship is. Well, it appears that they're perpendicular, right? It appears they are perpendicular. Right? They form right angles. And not only does it appear, but that is true. And it is one of the most crucial aspects about the relationship between tangent lines to circles and their radii, right? The radii and the tangent lines will be perpendicular. Here we go, tangents and radii. Any tangent drawn to a circle will be perpendicular to the radius drawn to the point of tangency. All right, now, how do we prove this? Well, the key to understanding this remarkable fact comes from a concept we saw back in unit number 4. Let's take a look. The distance from a point to a line. The shortest distance from a point to a line is the length of the perpendicular segment between the point and the line. All right, so in other words, like forget about this picture for a second, right? If I had just some random line and a point not on the line, okay, and I said, hey, draw for me the shortest path between this point and this line, that shortest path would be perpendicular, the line segment that goes from that point perpendicular to that line, okay? Now, that being said, right, let's take a look at exercise 2. Locate a point D anywhere on line M from exercise number 1. Draw in segment AD. All right, cool. Well, I'm going to actually put my point right over here. Okay? So you can kind of put your point anywhere you want, but I'm going to put it right over there. Okay, so pause the video now and get that drawn in. Okay, so let's take a look at letter A now. Why can you conclude that AD is longer than AB? So I claim that no matter where you put that point, anywhere you put that point and you connect the center to that point, that segment is going to be longer than that one. Pause the video now and see if you can give an explanation for that. Well, it's pretty simple, right? If you think about it, right? I could put another point on right there, right? It goes like this, right? AD extends outside of the circle, so must be longer than any radius of the circle. Okay? And keep in mind, right, the whole point of a tangent was that it only touched the circle in one location, right? That particular location. And therefore, if I identify any other point along that line, right, then obviously the length of that segment, right, is going to be longer than the length of that segment because that segment extends outside of the circle, right? So there's this portion that's being added on to the radius there. All right, letter B. How does this now allow you to conclude that the tangent line M must be perpendicular to the radius AB? All right, well, why don't you pause the video and see if you can think about how this piece of information, along with this fact from earlier in the course, allows us to conclude that AB must be perpendicular to line M. Take a moment. See if you can come up with your thinking even if you don't get it written down. All right, well, right, what we know is the distance from A to any point on line M other than B will be longer than AB. All right, so we know that. That's what we just kind of established in A. So the distance from A to any point on line M other than B will be longer than AB. But that means by default, this means AB is the shortest path from point A to line M. Let me move this out of the way. And this means AB must be perpendicular to line M, right? The shortest path from any point to a line will be along a line segment that is perpendicular to that line. And since this must be the shortest path from A to line M, it's got to be perpendicular to line M. Remarkable. And again, it only works because a circle is a collection of all points that are equidistant from that center point. If that wasn't the case, then there would be no way of knowing whether or not this was the shortest path or possibly that was a shorter path. But because, right, that length and that length are equal, and that extends past that length, then any point on this line has to be farther away from A than point B is, and therefore they must be perpendicular. Really, really quite cool. Now, all right, because tangents and radii have this perpendicular relationship, be mindful of problems involving the Pythagorean theorem or right triangle trigonometry when they're present in circle problems, okay? All of our caveats about, hey, there's a right angle, so all sorts of things could happen that involve right triangles can occur in this situation. Let's take a look at exercise number 3. In circle K, segment AB is tangent to the circle at point A. The radius of the circle has a length of 5 units, and the tangent has a length of 12 units. BK intersects the circle at point C. Letter A, what is the length of BK? All right, pause the video now and see if you can figure out the length of BK. All right, well, the key here is, because this is a tangent, right, and this is a radius, what we know is that this is a right angle. Now, because we know that's a right angle, then we know that triangle AKB or BAK is a right triangle. Now, what do we know? We know that the radius is 5. We know that the tangent length is 12, and so we can figure out the length of BK by simply using the Pythagorean theorem, right? So I'm just going to say, 5 squared plus 12 squared is equal to c squared. 25 plus 144 is equal to c squared. C squared is equal to 169. C is equal to the square root of 169, so C is equal to 13. And that is the length of BK. All right. Letter B, what is the length of BC? Well, pause the video and see if you can figure out how to find the length of BC. Take a moment. All right, well, it's easy enough, right? The plain fact is we know that BK now is 13, and we also know that KC is equal to 5 because it's a radius, right? And therefore, we can say that BC is equal to 13 minus 5, so BC must be equal to 8. All right, and that's simple enough. All this thing is really doing is forcing you to say to yourself, oh, I know all radii are the same length, and therefore, right, if that whole thing is 13 and I know a portion of it's equal to 5, the other portion must be 13 minus 5, or 8. Now let's take a look at letter C. What is the measure of angle K to the nearest degree? All right, well, let's take a look at what we have right now, right? What we've got at this point is we've got a right triangle. Okay, something that looks like this. We know that's 5, we know that's 12, we know that's 13, that's K, that's A, that's B, and I want to know the measure of angle K to the nearest degree. All right, anytime you're working within a right triangle and you're looking for the measure of an angle, right, you should consider, especially if they tell you to round, you should consider using right triangle trigonometry. Now, one of the tricky things at this point is that typically when we used right triangle trigonometry back in the last unit to solve for a missing angle, I always said to you, take a look at the angle, look at the two sides that you know, and set up a trigonometric ratio involving those two sides and the angle, and then use the inverse trig function, the inverse sine, inverse cosine, inverse tangent, to find the angle. The tricky part about this is that we know all three sides. The reason that's tricky is that means you can use any trig ratio you want. Any one of them you have enough information to set up. So pause the video now, set up one of the three trig ratios. Again, any one of them will do because you have all three sides. Then use the inverse trig function to figure out what that angle is. All right, well, I kind of like the tangent ratio myself, okay? So in other words, I know that 12 is opposite, 5 is adjacent, 13 is hypotenuse. So I could say that the tangent of angle A is equal to 12/5. So A will equal the inverse tangent of 12/5. And let's see what our TI Inspire gives us. We're going to go to trig, down to inverse tangent, not tangent, but inverse tangent. I didn't get it. There we go. Let's try that again. Inverse tangent of 12/5, and enter, and we get that to the nearest degree, 67 degrees. Again, probably the thing that is most challenging about this problem is that any one of the three would work. For instance, I'm not going to do all three of them, but I could have said the sine of angle A is 12/13. And then I would have known that A was equal to the inverse sine of 12/13. And when I do that, trig, inverse sine of 12/13, I get exactly the same answer, right? 67 degrees. So it doesn't matter in that case. Oh, am I?
It should be the tan, no, it should be the tan of K.
Oh, it should be the tan of K. I don't know why it's the tan of A there. That's weird. That's weird. I think I just like A as a letter. I don't know why. Thank you, Joey. Great catch. All right. Either way, right? The point here, the thing that maybe makes this a little bit more challenging is the fact that whenever we were doing those trig problems, not whenever, but most of the time when we were doing those trig problems in the last unit, you had only one choice. You had two of the three sides, and you were forced to use one of the particular ratios. In this case, any one of the three ratios will work. All right, let's take a look at another important fact that has to do with tangents. Okay, tangents drawn from the same exterior point. The perpendicularity of radii and tangents gives rise to another important fact about tangents, which we will prove in the next exercise. Let's take a look at that fact. Tangents to a circle from a point. All tangent segments drawn from the same exterior point to a circle will have the same length. And I should really just point out the following fact. If you have a point like point B that's exterior to circle A, there will always be two tangents that can be drawn to the circle. So maybe I should have said the two tangent segments drawn from the same exterior point will have the same length. And it may seem obvious to you, but we should prove it. So let's take a look at exercise number 4. In circle A shown below, tangents BC and BD have been drawn from exterior point B. We want to prove that BC and BD are congruent to each other. In other words, the length from this point to that tangency point and from that exterior point to that tangency point will be identical. So letter A, how could we prove that triangle BCA is congruent to triangle BDA? Explain. All right, so pause the video now and see if you can figure out which triangle congruence theorem you could use to prove that this triangle and this triangle are congruent to each other. Pause the video and take a moment to do that. All right, well first, we know that the tangents are perpendicular to the radii, so that gives us those two right angles, which are already in the picture. Another thing that we know is that AC and AD are congruent to each other because they're both radii, right? And finally, we know that AB is congruent to itself because it is a shared side. Now, AB happens to be the hypotenuse of those two right triangles, and therefore, triangle BCA and triangle BDA are congruent to each other by the hypotenuse leg theorem, right? So let's get all that down in kind of a paragraph-like proof, right? We know that AC is perpendicular to BC, and BD is perpendicular to AD, right? Ugh. The red always comes out when I don't want it to, okay? Because radii are perpendicular to tangents, right? Then we know that AC is congruent to AD because all radii are congruent. All radii of a circle are congruent. And then finally, AB is congruent to itself, maybe parentheses, that's reflexive. So triangle BDA is congruent to triangle BCA by hypotenuse leg, right? I've got their two hypotenuses equal, hypotenuse, that's not right. Hypotenuses are equal, right? And these two legs are equal, right? So the two right triangles are congruent by hypotenuse leg. And now, something we haven't done for quite some time, From the fact that triangle BCA is congruent to triangle BDA, why can we say that segment BC is congruent to segment BD? This is easy. Pause the video now and see if you can write something down. Well, now that we know these two triangles are congruent, of course BC is congruent to BD because they are corresponding parts of congruent triangles, right? In fact, we could just say CPCTC, right? Corresponding parts of congruent triangles are congruent. Easy enough, all right? And again, it's remarkable, right? The only reason that this is true is because of the beautiful properties of circles and the fact that AC and AD are congruent to each other. If AC and AD weren't congruent to each other, then there would be no way of knowing that this triangle was congruent to this one, and therefore there'd be no reason to know that BC and BD were congruent to each other. Now, this gives rise to kind of a classic problem that I've given you far too much room here to even do. This is going to be a simple problem, but let's take a look. Exercise number 5. In the diagram below, circle O is inscribed in triangle ABC so that it is tangent to points D and E and F as shown. If AD is 4, BF is 7, and CE is 6, then determine the perimeter of triangle ABC. Hey, before we even do this, let's just give a nod to the fact that we've seen this before, right? Not this exact problem, but we've seen this kind of diagram before, way back when we were looking at what was known as the incircle of a triangle, right? A circle that is inscribed inside of a triangle, or a triangle that is circumscribed around a circle, right? But now that we know these things are tangent, right? We know that AD is 4, we know that BF is 7, and CE is 6, right? The rest of this is quite easy, right? Because the tangents from any given exterior point are equal in length. So if AD is equal to 4, AE is equal to 4, right? And if CE is equal to 6, CF is equal to 6. And finally, right, if BF is equal to 7, BD is equal to 7. That then allows us to say, well, that's got a side length of 11, that's got a side length of 10, that's got a side length of 13. So the perimeter is 11 plus 10 plus 13, which is going to be 34. All right. And that's kind of a classic application of that particular problem. We'll see other applications as we kind of move through this particular unit, but that is a simple application. If we have a circle, right, the incircle of a triangle, and we kind of know those various lengths, then we can figure out other lengths based on that idea that the two tangents drawn from an exterior point to the circles have the same lengths. All right, let's wrap this up. So today we introduced a brand new concept, right? The idea of a tangent to a circle, a line or a line segment that no matter how far or long it's extended intersects the circle just one time. And what we proved, right, very important, was this relationship between tangents and radii that are drawn to the point of tangency. The idea that that radius and that tangent will always be perpendicular. And that gives rise to a variety of things. You know, a lot of right triangles get involved in these types of problems. What we saw in that last little piece, the two tangents will be equal in length from a given exterior point. All right, facts about tangents will kind of come into play as we move through this unit. So get some practice on the homework. Make sure to understand what a tangent is versus a chord, all right? Because in the next lesson, we're going to introduce the idea of a secant, right? So we'll have chords, tangents, and secants. Oh my. All right. I just, for now, want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.